Can you guys on Zoom hear me and all that jazz?
Yes, sir.
All right, so before class starts today, I would like to talk to you a bit about your exam, which is tentatively tomorrow. The first question I would like to ask you guys is, do you want your exam to still be tomorrow? Like, we could push it off till Thursday and I would have no problem with that.
That'd be great.
Yeah, I feel like I know that I put video stuff up there, but effectively me missing half of the talk on this whole transient analysis stuff, I feel like having an extra day to discuss those things with you and answer any questions that you might have might be of use to you guys. So the two people that are physically here don't seem to mind if the test is moved till Thursday. What about you two guys on Zoom?
Thursday is fine.
Okay.
Yeah, Thursday would be awesome.
All right, so I will move the first exam from tomorrow to the exam. Right now, only 2 people are regularly showing up physically to class. So what I am considering doing, because there are then roughly 5 students who are attending class virtually, is making the entire exam a take-home exam for everyone. So effectively what that would really mean is that it's just practically a homework set, and as much as you'd have a week to do it, it's just going to cover all the material we've covered at this point instead of one single topic. How does that sound? So as opposed to having a closed book 75-minute portion of your test that I'll have to figure out how to administer, and then also a open book take-home portion of your test. We just do everything as a take-home portion. Does that sound reasonable? Any problems with that?
That sounds fine.
All right. Okay, so to be clear then, we are going to move exam 1 from Tuesday to Thursday of this week. It will be, and all exams in this class will be completely take home. I got a bit overwhelmed last week with all the random stuff that I had to do outside of school stuff, and so I forgot to post homework assignments last week, with the exception of the parallel RLC circuit stuff. So I'm going to post a series RLC circuit set immediately after today's class, which will be due this Friday. And then I will also post a general RLC circuit analysis homework set, which will be exactly 2 problems. And that will be due 1 week from today. Does that sound reasonable? Plenty of time to get stuff done, because I think the parallel stuff is due today, right? Okay. All right, so I think we've covered all of the bookkeeping type stuff. So before we jump into today's lecture, which is more general RLC circuit analysis, so I hope you guys watched the first video on it. Does anybody have any questions or anything for me to knock out? Nope. All right. So let me share my screen and bring up the right thing. No. All right. So today we're going to talk about second order transient analysis. Where we have 2 of the same energy storage elements. All right. So for example, we might have a circuit that looks something like this. We have some voltage source, Vs. I'm going to say that there is a switch that is closing at t is equal to 0. Here's some resistor R1. Here is an inductor L1. Here is a resistor R2. Here is an inductor L2. And for the sake of argument, for this particular problem, we are going to try to figure out an expression for what I'm going to call V1 of t, which is the voltage drop over inductor L1, and an expression for V2 of t, which is the voltage drop over inductor L2. Let's say that our source voltage Vs is 1.4 volts. Our resistor R1 has a value of 0.4 ohms. Our resistor R2 has a value of 0.3 ohms. L1 is 0.1 henries, and L2 is 0.2 henries. So we're going to talk about a couple of different ways that we could approach this problem. All right. So the first way that we're going to approach this guy is effectively using a combination of Kirchhoff's current law and Kirchhoff's voltage law and things like that, kind of a kitchen sink approach. So what I'm going to do is I'm going to identify my inductor currents as well, because we're going to have to keep up with those guys. So I'm going to call this current flowing down through inductor L1 I1, and this current flowing down through inductor L2 I2, and this current flowing through resistor R1 during the transient condition, I'm going to call Ix of t. So if I apply Kirchhoff's current law at the node that connects R1, R2, and L1, I will find that, so applying KCL. Actually, before I even do that, did you guys watch the Thursday video at all? So do you know what the hell it is that I'm trying to do? Let's start there. Any thoughts at all on what I'm trying to do at this point in the circuit analysis?
You were trying to replace equations to where you can have first order and second order derivatives in terms of one of the variables.
Okay, so the suggestion, which is pretty close, is that I'm trying to get first and second order differential equations so that I can make some substitutions. That is the process that I'm going to go to, but what I am looking for is a second order differential equation of the form. So I want either something like this, the second derivative of I1 plus, I'm trying to remember, I think I called this B, times the first derivative of I1 plus C times I1 is equal to K, where K is some constant, could be 0, doesn't necessarily need to be, or the exact same type of expression A second order differential equation could be homogeneous, but doesn't necessarily have to be in terms of my second variable, which is my inductor current through inductor L2. So plus B di2 plus C is equal to K. Now, it literally does not matter if I wind up with a differential equation, second order differential equation, in terms of the variable I1 or in terms of the variable I2. I will wind up with the exact same value for B, the exact same value for C, and the exact same value for K. So it literally doesn't matter. So if we have a capacitor and an inductor, it doesn't matter if we put things in terms of the capacitor voltage or the inductor current. Here, since we have two inductors, it could be the current through inductor 1 or the current through inductor 2. The reason why we have to go through this approach of finding the differential equation itself is because this is not a simple parallel RLC circuit or a series RLC circuit. Can't be either series or parallel RLC because there's no capacitor to begin with. So it's not an RL circuit either. Even though it's imposed entirely of resistors, and we can combine those resistances. Also, there is no way we could combine those inductances. So because we are treating this as a second order circuit because there are two energy storage elements, we have to come up with some second order differential equation to describe what's going on. All right, with that out of the way, now let's apply KCL. All right. So I could say, hopefully fairly easily, that Ix of t is simply I1 of t plus I2 of t. The current entering that node in red, Ix of t, is equal to the current exiting the nodes in blue, I1 and I2. Nothing particularly wild or crazy there. So we have one equation already that has some relation to the two currents. So our problem here is that we need to get Ix of t, the thing on the left-hand side, we need to get rid of that and somehow get a different relationship that expresses it in terms of our current quantities of interest, I1 and I2. Any thoughts on how we might do that? And all of the equations that we're building are occurring during the transient condition. So after that switch has closed.
Would we use the voltage across the resistor?
Okay, so the question was, would we use the voltage across the resistor? Yes, but I think we're going to use it in a very specific way. And by that, I mean, we're going to write an Ohm's law equation. That's another way that we can get some relationships here. So for example, what I mean by that, the voltage drop, so if we're assuming the current Ix is flowing into the positive polarity terminal, meaning we want to keep the direction that we have, we could say that the voltage drop over that resistor R1 is Vs minus V1, right? Divided by R1 gives us Ix of t. So we're getting closer. How are we, so Vs is a constant. There's no way that we can ever express it in terms of these time varying currents. But what about that voltage V1? How could we express that in terms of our time varying inductor current or currents as is appropriate?
1 over L, the integral of the voltage is equal to the current?
So the suggestion is, okay, so let me think about this. So we know that IL of t in general is 1 over L, the integral. We might have some initial conditions and all that kind of stuff to pay attention to if we're paying attention to our initial conditions. The transverse of this relationship is this guy. I personally choose to avoid using integral relationships if at all possible. And because I'm looking for a second order differential equation where everything is in terms of derivatives, I'm going to actually use this guy here, right? So I could say that this is going to become, so let's say Vs over R1, I'm just moving my denominator and separating things out, minus V1 over R1, where V1 is simply L1 times the derivative of I1. Does that make sense? So it's a simple Ohm's law substitution there. We've used Ohm's law to come up with this equation and also the derivative-based relationship between the inductor voltage and the inductor current for inductor 1. So I'm going to put these two equations together. So let's call this guy 1 and this guy 2. And I'm going to substitute 2 into 1. And so what that is going to give me, so I'm going to have Vs over R1 minus L1 over R1 times the derivative of I1 is equal to I1 plus I2. And what I'm going to do now is I'm going to subtract I1 from both sides so that I have an expression that is just telling me what I2 is, right? So I could say that I2 of t is going to be negative L1 over R1 times the first derivative of I1 minus I1 plus Vs over R1. I'm going to call this guy 3. So now, effectively, I need to come up with a second relationship that involves I1 and I2 effectively by itself. Any thoughts on how I might go about doing that? KVL around the right loop. Perfect, okay. So if we do KVL around the right loop, right-hand loop, we would have negative V1 plus I2 times R2 plus V2 is equal to 0. And we can express both V1 and V2 in terms of those inductor currents, right? So this would look like negative L1 di1 by dt plus R2 I2 plus L2 di2 by dt is equal to 0. So let's call this guy 4. So this KVL around our right-hand loop equation has everything in terms of I1 and I2. And we could now substitute 3 into 4, or yeah, I think just direct substitution of 3 into 4 would be our best bet here. Yeah. All right. So substituting 3 into 4. So let's see, we're going to have negative, this is going to get large, negative L1 times the first derivative I1 plus R2 times I2. So that would be negative L1 over R1 times the first derivative of I1 minus I1 plus Vs over R1 plus L2 times the derivative of I2. And this will all equal to 0. So now we really just need to kind of go through some things here and distribute. So I'm going to leave this negative L1 di1 by dt here by itself because that's nice and easy. I'm going to distribute this common factor of R2 across this middle term. So that's going to look like negative. Come on, yeah. R2 L1 over R1 times my first derivative. Then I'm going to have minus R2 times I1. And then I will have plus R2 Vs over R1. Now I'm going to have to distribute L2 and take the derivative for this next bit here. So I'm going to have minus L1 L2 over R1 times the second derivative then I'm going to have minus L2 . times the first derivative of I1. And I'm going to have L2 times the derivative of a constant, so that's just L2 times 0. Set this guy equal to 0. And I can see that all of my terms involving I1 have a negative sign. My constant, which is R2 times Vs over R1, is the only thing with a positive sign. So if I move that constant sign to the other side of the equal sign, everything will be negative, and then I can get rid of that negative term. Or I could just move all the L1s to the other side, or I1s to the other side. So I'm going to do just that. So, and I'm also going to group like terms. So we're going to have the coefficient of L1 times L2 over R1 times my second derivative so that takes care of this guy. For my first derivative terms, I'm going to have a factor of L1 and R2 L1 over R1 and a factor of L2, right? Let me just look through this here again. So this guy is a first derivative term, this guy is a first derivative term, this guy is a first derivative term. So I'm going to have L1 plus L2 plus R2 L1 over R1 times the derivative of I1 with respect to time, which takes care of all of those guys. Then I'm going to have just plus R2 times I1 will be equal to R2 times Vs over R1. And now I'm almost in the exact form that I'm looking for, right? The only thing I need to do is divide both sides by a factor of L1, L2 over R1. So instead of doing that explicitly, I'm going to say that B, our coefficient of the first derivative term, is going to be L1 plus L2 plus R2 L1 over R1, this whole thing divided by L1 L2 over R1. Does that seem reasonable here? And C is just going to be R2 divided by L1 L2 over R1, which would allow us to say that alpha is just B over 2 based on Thursday's lecture, and omega naught is just the square root of C. So let's take a moment and calculate these values. So let's see. So L1 is 0.1, L2 is 0.2, R2 is 0.3 times L1 0.1 divided by R1 0.4 1, 0.1 times L2, 0.2 divided by R1, 0.4. Divide this by 2, 3.75. That's what I got. C will be a little bit easier. R2 was 0.3. L1 times L2, so that's 0.1 times 0.2. And then divide by R1, 0.4. Square root of 6. Radians per second. So first, did you guys get similar numbers? Okay. All right. So from this point, this problem becomes exactly like every other problem that we have worked. We would simply analyze a circuit at t is equal to 0 minus, t is equal to 0 plus, t is equal to infinity. And then now that we know alpha and omega naught, we can tell whether it is a critically damped, overdamped, or underdamped circuit, and it's just as easy as anything we've ever done. So instead of going through those motions, unless you want me to, I'd like to look at solving this type of circuit in a slightly different way. Which would you prefer? Okay. I don't know that this is going to be that much easier at all. So let's start. I'm going to redraw my circuit. Just full disclosure, this is still going to be nasty. It's just a slightly different way of looking at it. Here's my resistor R1. Here's my inductor L1, my voltage V1. Resistor R2. Bless you. L2, my voltage V2. And I'm still going to identify I1 and I2. Now, I'm going to do mesh analysis to solve this guy. So different way of looking at the same problem with slightly different relationships where we'll end up with the exact same solution. It may be easier for you guys to do it this way because you're more used to relying on mesh analysis to do things, because that's what all Circuits 1 students seem to love to do. So let's apply Kirchhoff's voltage law at mesh 1. We would have negative Vs plus R1 times IA plus L1. So we're doing the voltage drop, right? So we're doing we're effectively just adding V1, which is going to be L1 times I1, but we're going to express I1 in terms of these mesh currents. All right. So that would be L1 times the derivative with respect to time of IA minus IB. Is equal to 0. And so I'm going to rearrange this guy ever so slightly and say that I have R1 times IA plus L1 times the derivative of IA minus L1 times the derivative of IB is equal to VS. All right. And let's see. I'm actually going to change this again slightly. The IB only shows up once, right? So I can kind of isolate that guy, which will be useful. So another way to write this exact same expression would be R1 times IA plus L1 times the derivative of IA minus VS is equal to L1 times the derivative of IB. I'm actually going to do this one step further. I'm going to not do it. I'm going to divide both sides by that L1 factor as well to get just the derivative of IB by itself. Because that'll be easier to directly substitute in later. So let's call this guy 1. So R1, yep. All right. Now let's do KVL around mesh 2. See what falls out of this guy. So we're going to have negative V1. So I'm going to put this as L1 times the derivative of IB minus IA. So let's start. Does that make sense? So negative V1, where we know that this guy right here is V1, is the exact same thing as what I have written down here at the bottom, because I just changed the order of the subtraction, which is the same as multiplying through by a factor of negative 1.
The other one would be IA minus IB.
IA minus IB would give me positive V1, but I'm looking for negative V1. Because when I do KVL around this loop, I see the negative polarity terminal of V1 first. Then I'm going to have IB times R2. And then I'm going to have V2, positive V2, which will just be L2 times the derivative of IB. Is equal to 0. I am going to break this up a smidge here. So in terms of IA, I have negative L1 times the derivative of IA, right? Plus L1 plus L2 times the derivative of IB. Plus R2 times the derivative of IB is equal to 0. Right?
Why we didn't just do L times I. Oh wait, we did. It kind of confused me that we looked to the first equation to do VS or V1 rather than the mesh. I don't know why.
So we did use mesh. So we're following I2 around, okay? So there's a current of IB. So let's not say that we're looking at V1 at all. We're looking at the voltage drop over the inductor, L1, with the positive polarity terminal on bottom, okay? So that is going to be L1 times the derivative of the total current flowing up through the inductor, where the total current flowing up through the inductor is IB minus IA, which happens to be negative L1 times the total current flowing down, which we already figured out.
It makes sense now. I don't know why. It confused me when we were looking at
Yeah, no, it's weird. Like we're taking voltage drops. We're applying mesh analysis to inductors, which we've never done before. So it's absolutely understandable why it might seem a little wacky. So, yeah, I have no problem explaining it because I understand exactly why you're like, what the hell is going on? You've literally never done it before. So I got no problem whatsoever. But we're just using that exact same relationship that we used a moment ago. VL is equal to L VI by dt. We're now expressing that I as a combination of mesh currents. And depending on which way we want or where we want the positive polarity determinal to be, tells us whether we're going to have IA minus IB or IB minus IA, just like it would when we were doing regular old mesh analysis and following one particular current around the loop. All right, so I'm going to call this guy equation 2. Now let's look at what we have here real quick. So trying to think about things here. Now, obviously, we can't we can substitute 1 into 2, right? Because we have a derivative of IB with respect to time term in equation 2. But we also have a first or a 0th derivative term, the function IB itself, that we don't have a relationship for, okay? So I'm going to do something a little strange here, or potentially a little strange. I'm going to take the derivative of equation 2. I'm also going to wind up taking the derivative of equation 1, and you'll see why in a moment. So taking the derivative of equation 2. That is not how you spell derivative. That is going to give me, let's see, so I'm going to have negative L1 times the second derivative of IA with respect to time plus L1 plus L2 times the second derivative of IB with respect to time plus RL times the first derivative of IB with respect to time. So effectively, I know not all of you guys have had Math 245 before, but there's a method of solving differential equations where you effectively reduce the order of the solution. That's actually where where the critically damped response equation comes from. We are increasing the order because we know that we need to have a second order equation. And again, I am trying to avoid taking an integral like my life depends on it because I'm very bad at them. So I've taken the second derivative of 2. So now let's call this guy 3. Fairly obviously, I could substitute 1 into 3, but now I need to know what my second derivative is. So I've gotten rid of one problem by introducing another, but the problem that I've introduced here that I don't know what the second derivative of IB is actually pretty trivial because we can get that by just taking the derivative of equation 1. So if we take the derivative of equation 1, we're going to have R1 over L1 times the derivative of IA we're going to have the second derivative of IA we're going to have the derivative of that constant, which is nothing, is equal to the second derivative of IB. Let's call this. So now we know what the second derivative of IB looks like and the first derivative of IB looks like. And we have an equation that involves nothing but IA, the first derivative of IB, and the second derivative of IB. So we can substitute 4 and 1 into 3. All right. So we're going to have negative L1 times the second derivative of IA with respect to time plus L1 plus L2 times the second derivative of IB. So that's going to be R1 over L1 times the derivative of IA plus the second derivative of IA. right? And then plus RL times the first derivative of IB, which we got from equation 1, way up here, yeah. So it'll be R1 over L1. Sorry, that looks like an L. This should be a 2 because there is no RL. 2 and 2. So didn't want that to get super confusing and we forget what it is that we're talking about. All right, apologize for that. So R2 times R1 over L1 times the first derivative of IA. No, sorry, times IA. Plus the first derivative of IA. Minus VS over L1 is equal to 0. And now we're going to have to distribute things and all that kind of jazz again. So okay, so for our second derivative term, we have a negative L1, and then we have an L1 plus L2, right? So to me, that's going to be L1 minus Hey, I am not sure why Zoom decided to die. So let me reshare the screen. And if you see something that doesn't look right, let me know where to go back to. All right, nobody's saying anything, so I'm going to keep on trucking here. So we're looking for the coefficient for the first derivative term. All right, so there's obviously going to be an L1 plus L2 times R1 over L1 term. Then there is going to be a R2 term. So I'm taking care of this guy, where I distributed the L1 plus L2, and I'm taking care of this guy. Times my first derivative, so derivative of IA with respect to time. Now I have my 0th derivative term, so that's just going to be R2 times R1 over L1, I think. Yeah, R2 times R1 over L1 times IA will be equal to VS R2 over L1. And from here, I believe we can see that our B term is just going to be L1 plus L2 times R1 over L1 plus R2, all divided by R2. Excuse me, all divided by L2. And our C term, my pen thing all right, it is being difficult. Is going to be R2, so R1, R2 over L1, L2. And so alpha is B over 2, omega naught is square root of C, and let's take a moment to calculate those guys. So L1 plus L2, so that's 0.1 plus 0.2 multiplied by R1, which is 0.4, divided by L1, which is 0.1, plus R2, 0.3, divided by L2, 0.2, divide that by 2, 3.75 meters per second. So this guy matches R1 times R2, so 0.4 times 0.3 divided by L1 times L2, 0.1 times 0.2 is still the square root of 6 radians per second. So we solved it in two entirely different ways. We didn't even solve for our inductor currents technically in the second round. I mean, IA is actually the linear combination of our inductor currents, right? And we still were able to get the exact same coefficients for our differential equations, which means when we get into the nitty gritty of actually analyzing it and determining what it's, how it behaves, and getting our analytical solution, it literally did not matter which approach we took at all. So that's what I wanted to get through to you guys today, is you can do whatever wackadoo combination of nodal analysis, mesh analysis, KCL, KVL, Ohm's law that you want to do. Whatever makes the most sense to you is perfectly applicable. You will wind up getting the same answer if you are doing your steps correctly. If you are realizing your relationships correctly, you're good. Does not matter how you approach these problems. Anything that you can throw at it, including taking integrals, which I will not do, just to be very, very clear again, but including using the integral-based relationships, everything works because it's circuits, and that's kind of how these things work, right? That's probably the hardest part for most people to get about circuits, is that there's never one way to do it. There's usually 6 or 7. So yeah, it's and is it hard or is it tedious? Yeah, to me, again, I'm a jackass with a PhD who's been teaching this class for several years. None of the math that we do in these lower level classes is particularly difficult, but this algebraic combination and being like, oh God, okay, so like it took me a while working it this way to figure out, I have 2 first order differential equations with two variables, how am I ever going to introduce a second order thing in here? I'm forced to take a derivative somewhere, just kind of out of the blue, right? Because there was no way that I was ever going to get a second order relationship the way that I was approaching this. Because the mesh analysis is always going to give me just a simple first order relationship, because I'm always just dealing with the current and its first derivative. So getting fancy and throwing in an extra derivative kind of out of the blue just to satisfy a relationship, to me, was the hardest step of this particular analysis method. Writing the KVL equations takes a little bit of thought because we've never done a KVL equation using inductors before, but it mostly makes sense. But having the thinking skills to be like, I know that I'm looking for a second order equation, so how do I force this to behave as a second order equation? I'll take a damn derivative. That takes a little bit of extra effort, in my opinion. So that's what I had for today. So what I would like to do in class tomorrow morning, I'm going to post some homework assignments and all that kind of stuff. We might run through, literally, we'll work some homework problems together to kind of try to reinforce these things. Be like, okay, so what type of circuit is this? Is it series RLC, parallel RLC, or is it a general second order? And then go from there as to, all right, so now that we know what kind of thing this is, how do we go forward? And that kind of stuff. Does that sound like a reasonable use of tomorrow's class time? And we can also spend the last 15-20 minutes over, well, I guess I was going to say what should be on your equation sheet, but it's open book, or open book, open notes, so it doesn't matter what should be on your equation sheet, because everything that you've written down, plus all of my videos, plus the entirety of the internet is available to you. So.
Is it okay if, so, like, I did some homework that are due tonight as the general RLC rather than solving it as parallel?
There is no problem whatsoever in doing that way, except that it's just going to take you much longer. So one thing that we could discuss tomorrow is why you didn't think that they were parallel RLC circuits. Like how can we identify if it's a parallel RLC versus a series RLC versus a general RLC? My best guess is you probably did the ones with dependent sources as.
There was one that had like two switches. That
Okay.
kind of threw me off, where like a resistor was cut out or short circuited, and then an inductor. It was charging an inductor, but the capacitor and another resistor were like.
I think that was problem one, wasn't it? Yeah, we can talk about that one tomorrow.
Okay.
Yeah, no problem. Yeah, we'll talk about, I'll post, like I said, I'll post the homework assignments for series RLC circuits and general RLC circuits, and then we can spend the entire class just answering homework questions and or working homework problems, just to make sure that when you guys get your test on Thursday, that you'll have a week and a day to do or whatever, that everything makes sense, and that, I'm not saying you can't ask questions of me regarding your exams, but I'll probably be less forthcoming about your exam questions than I would be about homework questions, because they're supposed to be a better judge of what you know.
Are there any practice
Homeworks. I mean, so at this point, the exams are a homework set just over a wide range of material instead of one select topic.
Is it going to be due within one day?
No, it's going to be due a week.
Oh, okay.
Yeah. It's literally a homework set just over all the topics we've covered instead of one topic at a time. So I always made the take-home portion of my exams due a week later, just because students have stuff to do, or maybe they didn't do super hot on the in-class portion and need time to rethink and review and all that kind of stuff before they take the take-home portion. But with the class the class attendance being as disjointed as it is, where it's the two of you guys that show up physically, and then the other 5 guys that show up virtually, I don't know how to proctor that correctly. Like it doesn't, so it just seems easier on everyone involved to just do a take-home test for everything. So,
Oh, I had a question from, almost 5, leaves me off. This is real quick.
sure,
It's about, the practical model.
okay,
So when we apply the practical model, we throw out the, ideal assumption, right? Like, the, R in is it infinite,
correct.
so we use the actual value of R.
That is correct.
Mhm.
Yeah. So when we're using the practical model, you're absolutely right. We can't say that Rn is infinite so that there's no current flowing through. We can't say that the gain is infinite so that the voltage at the inverting terminal and the voltage at the non-inverting terminal are equal. All that gets thrown out the window. We have to redraw our circuit and effectively use nodal analysis. For better or for worse, usually for worse. Anything else? All right, see you guys tomorrow morning. Have a great rest of your day.
We're gonna be using a lot of Cal 3, vectors,
In this class,
like future classes.
yes. Specifically, you'll do a whole heck of a lot of, so your E&M classes is all vector calculus. Every last bit of it. Yeah, I usually, when I was teaching the E&M classes, I spent probably the first week and a half on just like math review. Then we got into the actual stuff. And then when I taught it's 313 now, but it was 311 when I did it. Yeah, I spent about 10 days on a math review. And then when I taught 411, which was the next class, I still spent the first 10 days on the math review again, because you guys suck at math.
Oh, we do.